Hey everyone, welcome into lecture number 16 of differential equations. This is the second part of the lecture on power series solutions to second order linear homogeneous differential equations. So let's start this lecture by remembering the form of a general second order linear homogeneous equation. So we will consider a differential equation of the form, and we'll give this equation a name so that we can refer to it later, but it's going to be p of x y double prime plus q of x times y prime plus capital R of x times y equals 0. And like I said, we'll call this equation star. All right. And we want to consider this equation now near a singular point. So we want to consider this near a singular point, x naught. And recall from the previous lecture that if p, q, and r are polynomials, so I'll write this out this way, but if p, q, and r are polynomial functions, so I'll just say polynomials with no common factors, so no common factors at all. Really what we mean there is that p has no factors in common with q and r, but I'll just leave it written like this, with no common factors, then in this case the singular points of the differential equation, so here the singular points are the points x naught, right, we call this x sub 0, such that p of x naught equals 0. So for which the leading coefficient is equal to 0, right? So these are going to be the singular points of the differential equation when these functions p, q, and r are as nice as possible in some sense. And for the most part, those are the kinds of functions that we are going to study. Okay, the kinds of coefficient functions that we are going to study. So as an example of a singular point of a differential equation, and trying to solve an equation near a singular point, let's refer to an example that we've seen before. And these are Euler equations. So you guys hopefully remember what Euler equations are. I'll title this one Euler Equations Revisited. And remember that an Euler equation is a second order differential equation that's of the form x squared times y double prime plus alpha times x y prime plus beta times y equals 0, where these Greek letters here represent just constants, right? So these are constants, real constants. All right, you probably remember from our previous study of Euler equations that the form of the solution of an Euler equation is x to the power r, right? So in some sense we guess, right? This is how we came up with this solution in the previous section, but we guess that the form of the solution to this equation. By the way, I should point out, how does this fit into the current situation, right? Well, x equals 0 is going to be a singular point because these coefficient functions are polynomials, and x squared is equal to 0 when x is equal to 0. So x not equal to 0 is a singular point for every Euler equation when it's written in this form, right? So now that we know this, now we get that the form of the solution is going to be y equals x to the power r, and our job is to determine that power r. And remember that actually when we do this, we think about this, we've studied this before, so I'm just going to write this down, but we think about this x to the power r as actually being e to the power r times natural log of x, and we'll put the absolute value there. In this scenario, then, this equation, it can be extended to values of r that are either irrational or even complex, because we have a way to understand e to a complex power, right? So values of r that are either irrational or complex. For rational numbers, this is just a perfectly fine power function, right? Power function. But let's write it down. Let's think about this one. We'll use this form, y equals x to the power r, to try to find the form of our solution. Or to remember, we'll do it again. We've done this before, but to do it again to find the form of our solution. And then at the end, we'll think about the different possibilities of the values of r, and then at that point, we'll utilize this exponential form of our solution. All right? So plugging into the equation, we take a couple of derivatives, right? So we say, all right, our solution we think is of the form y equals x to the power r. The derivatives are then y prime equals r times x to the power r minus 1. And y double prime is r times r minus 1 times x to the power r minus 2. And then we plug these into the equation, to this differential equation up here, and we end up with x squared times r minus 1 times x to the r minus 2 plus alpha times x times r to the times x to the r minus 1 plus beta times x to the r equals 0. And I'm sure you remember that now the powers of x combine to all be powers x to the power r at every spot here, and we can factor that out. So this then becomes x to the power r times r minus 1 plus alpha times r plus beta. And that whole thing equals 0. And so the characteristic polynomial, this is called the characteristic polynomial of every Euler equation that's given in this form with a leading coefficient of 1, right? If it has a leading coefficient of 1, then every 1x squared, right? If you think of the coefficient function of the differential equation, but 1x squared, every Euler equation of this form then has a characteristic polynomial of r times r minus 1 plus alpha times r plus beta. And of course, we're looking for values of that polynomial which set it equal to 0, right? Values of r for which that's equal to 0. And those are called the characteristic roots. And of course, just based on the quadratic formula, those solutions are going to be r1 and r2 are going to be equal to, I'm just going to plug into the quadratic formula. Now to do that, you have to rearrange a little bit. You distribute this, right? And then you're going to get r squared plus alpha minus 1 r plus beta. And so the solution here looks like negative parentheses alpha minus 1 plus or minus the square root of alpha minus 1 quantity squared minus 4 beta all over 2. All right, so just by plugging into the quadratic formula, these are the values of r. So if r1 and r2 are real and distinct, right, meaning different, so if they're distinct real roots of this equation, then the general solution of our Euler equation, so let's give this one a name as well, call this equation 2 star. The general solution of this equation 2 star is then just going to be what? So general solution of 2 star is y equals c1 x to the power r1 plus c2 x to the power r2. All right, so that's the solution. And by the way, this is only defined, so remember x equals 0 is a singular point, right? But this is defined on any interval now. This is the solution on any interval that does not contain x equals 0, because obviously if you plug x equals 0 into here, you're going to get 0 plus 0. It's just going to be 0, right? So this is true on any interval not containing x equals 0. But any other interval, this will be the solution. Okay, there are two more possibilities of the form of the roots, though. So what about if r1 equals r2 is a repeated real root? Well, we know what that means, right? That means that y1 is equal to x to the power r1. But y2, what do we have to do for y2? y2 can't be this, right? So this is going to be then e to the power r1 ln of x, right? And so then just by using what we know from our previous studies of second order linear constant coefficient equations, if we have e to the rt as one solution, then t e to the rt is another solution. So essentially what am I saying we should do? We should treat this ln of x like a t, right? So our second solution should be t e to the r1t. But then plug in what they are again, right? So then this becomes ln of x, I'll put the absolute value here, ln of x e to the r1 ln of x, but that's just equal to the following. So this term is just x to the r1, right? So x to the r1 times natural log of x. So those are the two solutions now. The two solutions are y1 is x to the power r1, and y2 is x to the power r1 times the natural log of x. So now our general solution is going to be y equals c1 x to the r1 plus C2 x to the R1 times the natural log of x. And again, this is going to be the solution on any interval that does not contain x equals 0. All right. So obviously if that interval's got only positive numbers, you can drop the absolute value there, but we'll leave it for the sake of the solution. But on any interval not containing 0 again. All right, and then the last possibility is that the roots are complex, right? Complex conjugates. So we'll say it this way. But finally, if R1 and R2 are equal to lambda plus or minus I times mu, so these are complex conjugate roots. So the whole point here is that mu is not 0, right? So we'll say it this way, with mu not equal to 0. Then remember, in terms of t, if these were in terms of t, right? So we'll do the same kind of deal here, but letting t equal ln of x again. All right, then the solutions are e to the lambda t times cosine of mu t, and so let me write I'll write it this way, sorry. So the solution, the general solution is the following. So it's going to be y equals c1 e to the lambda t cosine of mu t plus c2 e to the lambda t sine of mu t. All right, but again, we want to get this in terms of the x value, right? So we need to plug back in this natural log of x where the t is. For the exponential terms, that's going to leave us with x to the power lambda. And the cosine terms, we just have to plug this natural log x inside of the cosine function where the t is. All right, so finally our general solution here is going to be c1 x to the power lambda times cosine of mu times the natural log of x plus c2 x to the power lambda times sine of mu times the natural log of the absolute value of x. All right, and once again, this is valid on any interval that does not contain the origin. All right, so this is the solution on any interval not enclosing or not containing x naught equals 0. All right, so that's one way to solve well, if it's an Euler equation, it's a very specific example, right? But this is the one way to solve a differential equation, second order linear homogeneous differential equation near a singular point, right? So we want to solve these near the singular point. On this one, we solved it on any interval that does not contain the singular point. So that includes all the intervals that are half open intervals, or even open intervals that look something like 0, capital A, or capital B, 0, something like this, right? So the intervals that get right up next to the singular point but don't actually include it. And so these are the solutions of those Euler equations in every case of the possibilities of the form of the characteristic roots, right? Okay, so let's move on then. So now what we would like to do next is kind of generalize this idea again. So let's consider equation star again. And I'm actually going to rewrite it, but that equation, remember, was p of x y double prime plus q of x y prime plus r of x y equals 0. And again, we want to consider this near a singular point. So here x naught is going to be a singular point. All right, I'm going to give a definition here, kind of a double definition, but here's what it says. I'll start with the more general version. So definition, the following is going to be true. The point x naught, this is the definition, so the point x naught is said to be a regular singular point. So now we're already assuming that it's a singular point, okay? So x naught is already assumed to be a singular point. it's going to be a regular singular point, all right, if and only if the following functions, which I'll write out on different lines here, but x minus x naught times the rational function q of x over capital P of x. This is, sometimes we call this the function little p of x, right? And similarly, x minus x naught squared times the rational function r of x over p of x, if these functions have convergent Taylor series centered at x naught. So if and only if these functions have convergent Taylor series centered at x naught, right? So meaning that we have some interval x minus x naught less than rho, where rho is a positive radius of convergence here, where these two functions have convergent power series. Okay, now I'm gonna write down a more specific, a less general, so a more special case of this. So a special case of this definition, which we're actually going to probably use more often. Okay, so if P, Q, and R are polynomials, then this criteria about the power series, the convergent power series existing, this criteria implies the following. So implies and is implied by. So in other words, I'm going to replace this statement about the convergent Taylor series with two limits actually. So the limit as x approaches x naught of this difference x minus x naught times the function q of x over the function p of x, and the limit as x approaches x naught of x minus x naught quantity squared r of x over p of x. These limits should both exist and be finite. So if they both exist and are finite, so let me say this, if these limits both exist and are finite, then x naught is regular. Remember, it's already assumed to be a singular point, right? So if it's a singular point, you take these limits, then it's a regular singular point. All right, so there's a definition of a regular singular point. Now let's take a look at an example. So for this example, I would like to determine and classify as either regular or irregular. Irregular is obviously going to be not regular, right? The singular points of this is called the Legendre equation. So singular points of the Legendre differential equation. So this Legendre differential equation is given by 1 minus x squared y double prime minus 2 times xy prime plus alpha times alpha plus 1 y equals 0. And here alpha is any real number. So, but the point, all we care about for this example is that it's a constant, right? Alpha is a constant. So first of all, we need to find the singular points, right? These are, again, polynomial functions. So all we really have to do are find the roots of this coefficient function capital P of x. So the singular points themselves are going to be the points that satisfy 1 minus x squared equals 0. And obviously that's going to mean that x is going to be plus or minus 1. So those are the two singular points of the Legendre differential equation. And now we need to test to see, we'll take these limits. We'll use this limit method to test and see if they are regular or irregular, right? So let's start with x equals 1. By the way, if either limit does not exist or is not finite, then we can automatically say that the singular point is irregular. So if you do one of them and it doesn't exist, you can stop, right? You can say it's irregular. To show that it's regular, you have to compute both, actually, right? We have to compute both of these. So let's start with x equals 1 then. So we need to compute the limit as x approaches 1 of x minus 1 times the ratio of negative 2x, that's q, over p, over 1 minus x squared. And see what we get. Well, this factors in the denominator, right? So this is, and this minus sign can go here. So this can be written as the limit as x approaches 1 of 1 minus x times 2x over 1 minus x times 1 plus x. Those cancel, right? So this is the limit x approaches 1 of 2x over 1 plus x, and this is going to be 2 over 2. So that's 1. All right, so that one's good, but we cannot yet say that this singular point is regular. We now have to compute the limit of the second ratio, right? So the second limit is the limit as x approaches 1 of, this time it's going to be x minus 1 quantity squared. And then we can plug in. So r of x, which is alpha plus times alpha plus 1, it's constant, over this term, 1 minus x squared. All right. This time, what's going to happen? Well, we can factor again, right? So the limit as x approaches 1, whoops, I want to make sure this is all together here. So this is going to be x minus 1 quantity squared times alpha plus 1. And in the denominator, we have 1 minus x times 1 plus x. One of these will cancel. It's going to leave a minus sign, right? Which I'll group with that because it's got to flip the order here. The other one on the bottom, right, is not going to be an issue. And so now when we plug in, we get 0 over 2, and that's 0, right, which is finite, and it exists. So therefore, x equals 1 is a regular singular point. All right, I'm going to leave x equals negative 1, so the other singular point, I'm going to leave that for you guys as an exercise. You can pause the video right now and work that out. It's going to be extremely similar to this. The cancellation, you're going to end up with x minus a negative 1, so x plus 1 right here. Otherwise, and then you'll see how it cancels, right? But otherwise, it's going to be exactly the same. You'll get slightly different limits, but it's going to be exactly the same argument. And you should be able to show that negative 1 is also a regular singular point. So the next thing that we'd like to do is try to solve equations that are not Euler equations near a regular singular point. So we're going to take this Euler equation approach as a kind of a model for how we're going to solve these. So let's see how this is going to work. First of all, let's consider that we have the same equation. So let's consider equation star again near a singular point. Near a regular singular point. So we're going to use our definition of regular singular point here to help us, but near a regular singular point, which we'll call x naught. So we have a couple of things now. So first of all, we have our equation p of x y double prime plus q of x y prime plus r of x y equals 0. And because we're near a regular singular point, then we can write this, we can divide through by p of x near that point, right? So we can divide through by p of x near this singular, the regular singular point, x naught, and we can write this in the following form. We can now write this equation as y double prime plus little p of x y prime plus little q of x y equals 0. And so here we have the following. So now our little p of x, which is equal to capital Q over capital P, and little q of x, which is actually equal to capital R over capital P. I know it's confusing, but these both have, by our definition of regular, right? If we scroll back up, by our definition of regular, these both have convergent power series centered at x naught. So convergent Taylor series centered at x naught. So these have convergent power series representations at the regular singular point x naught. So now at this point, let's use the definition of the regular singular point again. We can scroll up and see that the regular singular point says that these two functions, x minus x naught times this is our function little p, and x minus x naught squared times our function little q, those two functions have convergent Taylor series, right? So we can now write that since x naught is a regular singular point, right? Then the following functions have convergent power series. So then the function x minus x naught times little p of x can be written as a convergent Taylor series, right? Centered at x naught. So it will write its coefficients as p sub n, and then its powers are x minus x naught to the power n. So this whole thing can be written as p sub 0 plus p1 x minus x naught plus p2 times x minus x naught squared, etc. And then similarly, x minus x naught quantity squared times q of x is also a convergent power series. That's the definition that we wrote down for regular singular points, right? So then this one is going to be q sub n times x minus x naught to the power n. And so if you write out the first few terms, it's going to be q naught plus q1 times x minus x naught plus q2 times x minus x naught squared, etc. And what you'll find then, if you just look at this and you work this out, right, is that p naught is actually equal to the limit as x approaches x naught of that limit that we wrote down up above there, right? So it's equal to this. And similarly, q naught is equal to the limit as x approaches x naught of x minus x naught squared times little q of x. Has to be, right? It's a constant term of these Taylor series expansions. That first term is always equal to the value of the function, which is in this case the limit, right? Convergent Taylor series. All right, so now what we can do is we can plug this into our differential equation. But at this point, just to keep our computation a little bit cleaner, we want to make another assumption now. So let's now, everything we've done now is for a general regular singular point, right? But now let's assume that the singular point, the regular singular point, is at the origin. So x equals x naught, x naught equals 0, sorry, is the regular singular point. Okay, and so then we can plug these into our differential equation. And let's see what happens. So plugging these power series representations it's going to be x naught equals 0 now, right? Into the dE, we obtain, so it's now going to be y double prime plus little p of x times y prime plus little q of x times y. That's going to become y double prime, it equals 0 obviously, right? But this is going to become y double prime plus power series. So here's what we need to do actually. What we want to do is not only when we plug it in, so if this is equal to 0, then this implies that if we multiply the whole equation by x squared, then that will still equal 0, right? So this implies that x squared y double prime plus x squared times p of x y prime plus x squared times q of x times y also equals 0. And so then what we can do is we can factor out some terms to get the functions that we need to get our power series, right? So to get our power series involved in this differential equation, we need these two functions. So in this case, it'll be x times p of x and x squared times q of x. That's this one we have. This one not quite, right? We need to factor out an x. So we can write this then as x squared y double prime plus x times p of x. There's our convergent power series times y prime plus this one, x squared times q of x, that's our convergent power series, times y, that's equal to 0. And now if we plug in our power series, right, then what we get is x squared, y double prime, plus x times, just plug in, I'm going to plug in the expanded version, so it's going to be p naught plus p1 times x plus p2 x squared plus p3 x cubed, etc., all times y prime. Plus, over here we have q naught plus q1 x plus q2 x squared, etc., times y. That equals 0. And at this point, let's think about what would happen if p sub n equals 0 for all n bigger than or equal to 1. And the same thing for q of n, right? Q sub n, what if that equals 0 for n bigger than or equal to 1? Well, what would that leave? It would just leave these coefficients, these p0 and q0, right? In this case, we obtain an equation that looks like x squared y double prime plus x times p0 times y. So I'm going to rewrite it as p0 x y prime, that's y prime, right? Plus q0, that's left here, q0 y equals 0. And what is this? This is an Euler equation, right? So this is an Euler equation. And we know how to solve those. We just reviewed how to solve those, right? So the solution of this, I'll write the solutions of this are of the form, what? Y equals x to the power r for some r, right? For some r. So that solves the Euler equation where we have ignored all of the other terms of these power series, right? That's obviously not going to be the correct answer, but what we can do then is we can regard these coefficients now as being like coefficient, what we can call, our text calls these coefficients the Euler coefficients of our differential equation. So here's what we do. So you can factor out the P0 and the Q0, which is what we want from here, right? Factor those out and then look at the rest of the series that's left there. So the terms P sub 0 times 1 plus, and then the rest of it is going to be P1 over P0x plus P2 over P0 x squared, etc. And then Q0 times 1 plus, same deal, right? Q1 over Q0x plus Q2 over Q0 x squared, etc. These are power series which, if you ignore the first terms, obviously are the coefficients of this Euler equation that we just solved, right? And so these are the Euler coefficients. The Euler coefficients of the differential equation. All right, and they're obviously written in power series. So all of this effort here is to do two things. One thing is to notice that by looking at only the first term, the constant terms of our power series expansions of these coefficient functions for the regular, right, that we get from assuming that our singular point is regular, if we look at only the constant terms of those, then we get a Euler equation which we can solve, right? That will solve the Euler equation. It will not solve the original differential equation in most cases, right, unless it was already an Euler equation to start with. So it probably won't solve this equation unless this was already very special, right? So what are we going to do? Well, what we can do is we can assume that our solution of the equation 3 star up there is going to be equal to y is going to be equal to x to the power r times some power series. All right, so we're going to assume that we have right here we have this equation when we write it out, right, looks like an Euler equation times some power series. So we assume that our solution is also of the form of an Euler solution times some power series, right? So this is the main idea here. So we then seek solutions to that equation 3 star of the form of Euler solutions. Those are the ones we've been talking about here, right? So Euler solutions times power series. All right, so those solutions will then look like y equals x to the power r times a power series centered at that singular point, which in this case is 0, right? So n equals 0 to infinity, a sub n, x to the power n. And so at this point, we can then multiply in the x to the power r and combine this into a single power series. Now, keep in mind that this r doesn't have to be an integer. This r could be, it could even be irrational, or it could be complex, right? So when this goes in here, this is going to change. I mean, it's still a power series, but it changes the powers so that they might not even be integer powers of x anymore. It's going to become a sub n times x to the power r plus n, or n plus r if you wish. All right? And so this is the kind of solution that we're going to look for, centered at a singular point. So a power series centered at a singular point of our differential equation. So again here, this is where x to the power r is a solution of the corresponding Euler equation. All right, so this is our goal, to try to find a solution like this. Once we know to look for a solution like this, then we can basically just follow all of the same steps that we've worked through in the last lecture, power series solutions. Right, we're looking for a power series solution where the powers are shifted a little bit by these Euler solutions. All right, so to see how this goes, let's do kind of a motivating example. I'm not going to do every single step of the thing. I'm going to do what's new. So I'm going to work through the new parts, and then leave the rest of this for you to finish. But we'll get through almost all of it actually. So here's our example. This is going to be called the Bessel equation. So many of you who are engineering majors have probably worked with the Bessel functions and the Bessel equation before, but this is the Bessel equation of order 1. It's given by the following second order linear differential equation. So it's x squared y double prime plus x times y prime plus, and then this is the part that makes it not be Euler, but x squared minus 1 times y equals 0. All right, so I'm going to do a couple of steps here. I'm going to work through this as kind of a motivational example. So I'm going to do a couple of steps here that actually we won't need to do every single time that we want to solve one of these equations at a regular singular point. But the first thing I'm going to do is make sure that the singular points are regular. Well, so the point is 0, right? So the only singular point is 0. So let's make sure that that's regular, and then we'll go through the steps of solving the Euler equation, and then we'll use that to plug into our series solution that we're going to seek. So step 1 is I want to make sure that these things that this is really regular. So verify that x equals 0 is indeed a regular singular point. So what do we need to do? Well, we need to compute the limits as x approaches 0 of, in this case, x times x over x squared, right? Q over p. And this is going to be, of course, equal to 1. And then the other limit that we need to compute is as x approaches 0 of x squared times this one. So x squared minus 1 over x squared. And so as we take this limit is going to be negative 1, right? So these cancel, and then 0 minus 1. So this is negative 1. And remember, this term is actually, we've already talked about this, this is our P0, and this one is our Q0. Right? So this is our P0 and our Q0. The point, though, that to make sure that it's regular, the point of checking this here was to verify that those two limits exist and they're non-zero. So that's step 1, to verify that the point x0 is indeed regular. So we've done that. Step 2, this is the one that we won't have to do in the future, and we'll see why, but we're going to do it now. So we want to make sure that everything we claim later is truly going to be true. But the Euler equation for this that corresponds to this is going to be, remember, the differential equation x squared y double prime plus x times p0 times y prime plus q0 times y equals 0. All right, we just computed p0 and q0, so this is going to be x squared y double prime plus x y prime minus y equals 0. All right, and then the characteristic polynomial of this is going to be r squared plus 1 minus 1 times r minus 1 equals 0, right? Always minus 1 when these are like this. So you have to subtract 1 from the middle coefficient. So that's just r squared minus 1 equals 0. And so our characteristic roots are going to be plus and minus 1. So those are our characteristic roots. All right, so I'm going to put a box around those, so just so that we remember these later. All right, and now from there we'll go to step 3. So there's the solution of the Euler equation. So this means that our solutions are going to involve x to the power 1 and x to the power negative 1, right? But the next thing that we're going to do is go to step 3. Step 3 is we are going to assume the solution is of the form that we talked about before. So we're going to assume that the solution is of the form y equals sum, n goes from 0 to infinity, a sub n times x to the power r plus n. And let's also assume at this point we don't know that r is one of these values, okay? So at this point, we're going to say, well, this could be for any r. We're going to have to determine r as part of our solution, even though we've already done it at the previous step, right? But we need to determine it at some future step, maybe we'll say. So that means in general also that when you take the derivative, you don't shift the index, right? Because this a sub 0 could actually be multiplied by a power of x. So what you get then is when you take the derivative, the first derivative is the sum from 0 to infinity of r plus n times a sub n times x to the power r sub n minus 1, right? Power rule still applies. And then y double prime is going to be the sum, n from 0 to infinity, of now r plus n minus 1 times r plus n times a sub n x to the r plus n minus 2. All right, so these are the function that we're looking for, the solution, its derivative, its second derivative. What do we need to do next? We need to plug them into our differential equation, just like we've done in the previous lectures, the previous lecture, I should say, for solving trying to find a solution of a second order differential equation by using series methods. So now we plug those in, right? All right, so we remember. So I'm going to write this down, but now plug in to the differential equation. All right, so I'm going to write down the equation. It was x squared y double prime plus xy prime plus x squared minus 1 y. Right, let me just make sure. Yep, x squared y double prime plus xy prime plus x squared minus 1 times y. Okay, so when we plug these in, what are we going to get? Well, this one goes here, so this is going to end up being x squared times the sum, n from 0 to infinity. I'm going to move all this so I have enough room to get it all in one line. All right, of r plus n minus 1 times r plus n a sub n x to the r plus n minus 2. All right, plus the next term is going to be x times sum, n goes from 0 to infinity, r plus n a sub n x r plus n minus 1, plus x squared minus 1 times sum 0 to infinity of just our power series, a sub n r x to the power r plus n, and that's all got to equal 0. All right, so now we can do some obvious things. Move this in here and move this one in here. That's going to shift those powers of x to just be r plus n, x to the power r plus n. And then this one we're going to want to distribute and send it in there twice, right? So now if we group all this together, what we end up with is the sum, n goes from 0 to infinity, of, we're going to have a bunch of stuff that's the same. So these ones are all going to start at 0, and they're going to have r plus n. So starts at 0, r plus n. Starts at 0, r plus n. This one with the minus 1 will start at 0 and have an r plus n. The one that has a x plus, this one when it goes in is going to make it x plus 2, right? Or r plus n plus 2 on the power of x. That one's going to be separate. So I'm going to combine the first three, well, the first, second, and fourth, right? And write this as follows: r plus n minus 1 times r plus n a sub n plus r plus n a sub n minus a sub n. Okay, plus now what's going to be left here is the sum, n goes from 0 to infinity, of a sub n x to the r plus n plus 2 equals 0. All right, I forgot something very important. I got all the coefficients here, but I did not, I wrote it this way because I was trying to factor out x to the power r plus n, right? Okay, so now it's right. So now it looks good. And what we need to do next is shift this one. So this one's going to shift how? It's got to go down to inside, so up to here. So this one's going to become the sum, n goes from 2 to infinity, of a sub n minus 2 x to the r plus n. Okay, that's what this one is going to replace this, right? All right, so if that's true, then what do we need to do? We need to pull out the first two terms of this one, right? Pull out the first two terms of this one, and then combine the sum starting at 2, because we're swapping this one out for this shifted version, right? Just like we did with the regular power series solutions. So when we do this, look what happens. We take out the n equals 0 term. Well, first, before we do that, we can combine this a little bit more. So this can all be combined here. It can be combined as follows. This is r plus n a sub n, r plus n a sub n. Factor those. You have r plus n minus 1 plus 1. So this whole term right here can be r plus n quantity squared a sub n minus a sub n, right? So this can all be r plus n quantity squared minus 1, right, times a sub n. So let me rewrite what we have here before we start trying to simplify it even more. This one's going to be the sum of r plus n quantity squared minus 1 a sub n x to the power r plus n. That started at 0. And this one is the sum. N starts at 2 to infinity. A sub n minus 2 x to the power r plus n. This whole thing equals 0. We want to combine these into a single sum, so we have to pull out the first two terms of this, right? So when n equals 0, this one's going to say r squared minus 1 a sub 0 times x to the power r, right? Plus, when n is 1, this one's going to be r plus 1 squared minus 1, right? A sub 1 x to the r plus 1. All right, plus then the sum, n goes from 0 to infinity of, now this all combines, right? So now it's going to be r plus n squared minus 1 a sub n, right? Plus a sub n minus 2. This sum starts at 2. It's very important. This sum starts at 2. Times a sub n minus 2, all times x to the power r plus n. This has to be 0. This entire sum has to be 0. So just like with our other power series equations, what does that tell us, right? Well, it tells us that this has to be 0 for all x. It tells us that this has to be 0 for all x, right? And then it tells us that this equation, this portion, has to be 0 for all x. Right? And so this is how we're going to get our coefficients here. The first equation, though, so the first equation here is actually very special, though. So this one, we'll see, so we'll say assuming a0 is not 0, and this is our free variable. So assuming that's our free variable, then x to the r can't be 0 either, right? Then r squared, we get what's called the indicial equation. I'm going to write that out. So then we obtain the indicial equation of the differential equation, and in this case it's r squared minus 1 must equal 0. And so this is how we get our values of r. This is how we get the values of r that are going to go into our solution. Notice this is exactly the same equation we set up here to remember this step, and that we didn't actually have to do this step separately. That's because it's exactly the same equation that we would get by solving the corresponding Euler equation. All right, and remember the Euler equation is the one that comes from the 0 coefficients, and so it's not a surprise then that it comes from the coefficient on the a sub 0 term of our solution, right? And so the indicial equation, this is called the indicial equation here, and you'll see that in the textbook, but the indicial equation is exactly the same as the characteristic equation of the corresponding Euler equation. And so we've already solved this for this one, but in general, you can skip that whole step 2. You should always do step 1 to verify that you're actually working at a regular singular point. But you can skip step 2 because it's going to come out of your calculation of everything else, right? And so at this point, you get that your r is got to be equal to plus or minus 1, right? And that your a0 is your free, it's free, All right. So you've got your one free coefficient, you've got two values of r, you're going to get two solutions. This one tells you, notice that r plus 1 squared minus 1 for these two values of r, that's not 0, right? So this part tells you that a1 must be 0. That's what this magenta highlighted portion tells you. And the rest of this gives you your recurrence relation, right? Because now we also know what r is, right? And so the rest of this gives us our recurrence relation, just like we were solving a power series equation for a power series solution in the previous lecture. So the recurrence relation is going to be, I'm going to rearrange it here, but a sub n should be equal to negative 1 over r plus n quantity squared minus 1 a sub n minus 2, and this is true for n greater than or equal to 2. So when n is 2 or greater. Okay. Notice that this relates 1 to the one that comes, so it relates the coefficients to the ones that come 2 previous to it, right? So that means that all the odd ones, because a1 is 0, this equation, the recurrence relation, tells us that all the odds are going to be 0, right? So taking this together with our recurrence relation, that's going to tell us that all the odd terms are going to be equal to 0. And then what you have to do is, for either value of r, just work out your solution of the recurrence relation just like you would do in the power series solutions that we discussed in the last lecture. So you make a table, write out n equals 2, 4, 6, 8, etc., and then try to notice a pattern. And you can do that for r equal to 1 or r equal to negative 1. And so I'm just going to tell you, so here, recommended exercise, this is where I'm going to leave off, but right, that's the recurrence relation, right? Just like we've talked about in our previous lecture. So work out the first few terms of the solution from the recurrence relation, all right, for either r equals 1 or r equals minus 1, and then verify that one of the solutions is of this form. No, I'll just write it, so not of the form, but one of the solutions turns out to be this following function, which is actually gets a name. It's called j1 of x. So this is going to be x over 2. So you factor out an x, but x over 2 times the sum, n equals 0 to infinity. That x that's factored out, by the way, is the, so that tells you exactly which one you're looking for, right? Let me finish writing it, and then you'll see. But negative 1 to the power n, so it's alternating. That's not a surprise. X to the power 2n, that's the evens only. So this is the power series portion, right? And then it's all divided by n plus 1 factorial times n factorial times 2 to the power 2n. All right? And so then you can see that this is the even terms plus 1. So that you're looking, this is going to be r equals plus 1. All right, but verify that this is the solution by solving this recurrence relation. Write out at least a few terms to at least verify that they should be in this form. And this equation gets a name, this function gets a name. This is the Bessel function of the first kind of order 1. Quite a name for a function, but that's the Bessel function of the first kind of order 1. And so that's derived by solving that comes from solving the Bessel equation of order 1 at its regular singular point and finding the series solution to that equation. All right, so there's some work for you guys to do in between these two steps, but at least write out the first few terms to verify that this Bessel function is indeed a solution of the differential equation. All right, I'm going to leave this lecture here, and I'll talk to you guys in the next one.